So we have seen a one-dimensional probability density function, right? Or a one-dimensional histogram. For example, if this was my petal length, I had my setosas here, I had my virginicas and versicolors like this, right? So my question here is, this is basically a one-dimensional density, right? This is basically a one-dimensional density plot. Now my question here is there something called a two-dimensional density plot or a three-dimensional density plot or an n-dimensional density plot? So let's look at what a two-dimensional density plot actually means. Okay, then of course we'll generalize it to 3, 4, n dimensions very easily. So let's go step by step. Okay, so here again the code is very simple. I just say Seaborn joint plot. I say on x-axis put petal length, y-axis put petal width, and I'm taking only iris setosas data here, right? And what I'll do here is as follows. Let me explain this plot for you. This is very interesting. It's a very interesting, it's a slightly more complicated idea than what we've seen till now, but once you get it, it's beautiful. Okay, my x-axis here is petal length. Remember, I've only taken setosa flowers. My y-axis here is petal width, right? So I got a scatter plot which looks, you remember we can draw a scatter plot, right? When you look at the scatter plot for this, let's look at petal length, petal width scatter plot from our pair plots. Okay, let's quickly go through it so that I can connect the dots for you much more easily. So here is my petal length on x-axis and petal width on y-axis, right? So this is my setosa, right? If you look at these points, of course, I'm drawing the multivariate density plot only for these points. Now, if you see, there are more points here in the center, and there are fewer points as you go away from the center, right? Because this is my petal length and this is my petal width. And the plot that I just showed you basically has points like this. You'll quickly notice that there are a lot of points in the central region. There are fewer and fewer points as you go away from the central region. Now we'll understand that in more detail. Just little patience and we'll get to it. But it's a very neat idea on how to visualize multivariate dimensions or two-dimensional density functions, right? So the way I plot this is as follows. Okay, so if I have, so your points will look like this, right? There are lots of points here. As you go away from the central region, there are fewer points, right? And as you go farther away, there are still fewer points, right? So the way this plot was drawn is as follows. Imagine, just like for your one-dimensional scatter plot, what did we do? If you had more points here, we increase the height of it, right? If you had fewer points here, the height is low. So in your distribution, if there are more points in this region, your height is more in your univariate density function, right? In your two-dimensional density function, what if, imagine there is a hill coming out of the screen towards you. Imagine that there is a hill coming out of the screen. Let me show you an example which will clarify it for you. So imagine that this is your petal length. Imagine that this is your petal length and this is your petal width. This is a three-dimensional plot here. Okay, and this is the hill that I'm talking about, which is coming towards you, which is the depth direction, right? So imagine if I draw a three-dimensional surface like this, where if I have more points in this 2D plane, I'm going to make the hill height higher. If I have fewer points, I'm going to make the hill height lower, right? That's one way to do it, because intuitively that's exactly what we did in a univariate density plot, right? Now let's go back to our plot here quickly, and what we're doing here is that since there are more points here, since there are a lot of points here in this region of petal length somewhere around 1.4 and petal width somewhere around this region, right? So what I'm going to do now is I'm going to build a hill. Imagine there is a hill here coming towards you from the screen, where the height of the hill is high here and the height of the hill is shallow here, right? Because this is a 2D surface, right? This is a 2D surface. So I'm trying to plot a hill that is coming out of the screen towards you, such that the height of the hill is very high here and the height of the hill is very shallow here. So in a three-dimensional surface, you'll see a hill like this, right? You'll see where these points correspond to this value, right? So, but this is 3D plot. Now, what are these lines? What are these colored dark blue to light blue? So those are called contours. Those are called contours. So these contour plots, so this is called a contour density plot. This is called a contour probability density plot. Okay, if you are actually doing a 2D density plot, you would actually get a picture. You need a 3D surface, right? This is your petal length, this is your sepal length, and the height corresponds to what is the probability of finding those points. But imagine pre-computers, people still plotted things like this with hand. right? So contour plots actually occurred in mapping, in geological surveys. So these plots you would see in when suppose I have a terrain like this. I have, let's say, 1 kilometer by 1 kilometer map, right? If there is a hill here, right, I would draw a contour map like this, right? Suppose there is a hill here, the hill center is here, and I would draw a contour map like this. This type of contour plots were actually very commonly used by geologists, by people who are doing surveying, civil engineers, etc. I know this very well because my dad is a civil engineer, and I've seen some of these plots when they were doing terrain maps and things like that. And what we realized quickly is, what this line basically implies is all these points on the line here have the same height. All these points here have the same height. That's how you create these circles. So what this circle represents here is all these points have the same height on the hill, on the probability hill. What this line says is all these points have the same height. And here what they've done, in addition to just drawing the lines, is coloring them. Darker blue basically implies that the height in this region is much higher than the height in this region. Okay, so this is called a contour probability plot. The quick thing that I can understand by just looking at this contour probability plot is, and again, look at it like this. These plots that you see on these two axes are nothing but the plot of, this is the distribution of petal width and this is the distribution of petal length for your setters of flowers. But so this is basically, this is again univariate distributions, right? So if you combine two univariate distributions, what you're getting is a two-dimensional distribution, and you can interpret two-dimensional distribution using contour plots. Again, just remember that the actual plot is coming towards you from the screen, and the darker it is, the higher that point is, right? And these circles or these boundaries that you're seeing all have the same height. It requires a little bit of imaginative skill and a leap of faith, but it's very, very straightforward once you get it. And here is a nice way to visualize it if you're doing 3D visualization. Okay, and having said that, I also wanted to explain it to you that these are useful. Like let's look at what we understand from here. What we understand from here is there are a lot of points with petal length in this region as well as petal width in this region, right? Which is super useful if you think about it, because most of my petal lengths are here and most of my petal widths are also in this region, right? So it's able to give us a sense of density in a two-dimensional space. Now your one-dimensional density is nothing but your PDF that we saw, right? And your two-dimensional density, your 2D density we saw using our contour PDFs, our contour plot, right? Our contour density plot. Now you might ask, what about 3D density plots, right? 3D density plots are much harder to visualize because we don't understand what the 4D looks like, right? So I can't tell you that, okay, imagine a fourth dimensional hill, because we've never dealt with it. But that's where mathematics comes into play. We will see in linear algebra how to learn anything in any dimension by learning things in 1D and 2D and 3D. Okay, till then, just bear with me. And this is called a multivariate density plot. It's a very, very simple idea, and we're using contours to tell us which all regions have the same height.